Hello everyone, today we are going to study ion exchange chromatography. Ion exchange chromatography is, as the name suggests, it involves the separation of ionizable molecules based on their total charge. Means, for the separation using ion exchange chromatography, the molecule has to be in their ionized state. Now, this chromatography relies on the attraction between oppositely charged stationary phase known as ion exchanger and the analyte. Means we have two things. First is the stationary phase, which is suppose for example positively charged. So this stationary phase will have attraction for an analyte which has to be oppositely charged. Means in case the stationary phase is positively charged, the analyte will be negatively charged. Now based on this, the ion exchanger consists of inner support medium coupled covalently to a positive or a negative functional groups. So we have the stationary phase. Stationary phase is known as exchanger. We have anion exchanger and we have cation exchanger, and to them are attached certain groups that we call as counter ions or the functional groups, which are of course oppositely charged. Now to these covalently bound functional groups, the oppositely charged ions are bounded mobile counter ion, which will be exchanged with like charge ions in the sample having charge magnitude more than the ions bounded to the matrix. So in this slide we come across three things. First is the matrix. To the matrix or the stationary phase is attached a counter ion, which is of course oppositely charged, and this when my analyte will be added, this counter ion will be replaced by my analyte. This I'm going to show in your next slide how it is done. So basically this ion exchange chromatography is used for the separation of charged biological molecules, which can be proteins, peptides, amino acids or nucleotides. Now as we know, amino acids make up the proteins and they are the zwitterides, means they have both the positively and the negatively charged group. Now depending upon the pH of the environment, the protein may carry a net positive or a net negative charge or no charge. Now when the pH at which a molecule has no charge is known as its isoelectric point or its pI. In a buffer with pH greater than the pI of the protein will carry a negative charge. Therefore, a positively charged anion exchange resin is chosen to capture this protein. Similarly, in a buffer with pH lower than the pI of the protein will carry a positive charge. Thus, a negatively charged cation exchanger is used. This is the diagrammatic representation which will clear all your doubts. This is the initial stage. Now you can see this is a matrix that we were talking about, or the exchanger or the stationary phase. This is positively charged. To this positively charged, we have these yellow colored functional groups, or we call them as counter ions. Now the charge on these counter ion will be negative, right? Now this is in the matrix. This is what we have added in the sample. Now this is positive, this is negative, and this negative counter ion will be replaced by my target. So this is in the next figure. You can see how the counter ion has been replaced by the negatively charged targets. These negatively charged targets are now binded. Now once we start the elution, different ions will, unbound ones will elute out of the column and only the negatively charged ones will remain binded to this column. In the figure, a positively charged, this is an anion exchanger because it is actually exchanging the negative ions with the sample. So that's why it is known as anion exchanger. With counter ions on its surface in the starting state. In the second phase, the binding of ions to be separated take place. At the start of the elution, weaker binding ions are deabsorbed. At the end of the deabsorption, the stronger ions are also displaced, and during regeneration, the starting state can be reconstituted by washing the column with the starting buffer. So once all the ions has displaced, this column is regenerated. This is how the workflows goes. First, we load the impure protein sample onto the ion exchanger. The column is washed to remove the undesired protein and impurities. The protein of interest is eluted either by change salt gradient or change in pH. Now, when you change the salt gradient and when we change the pH, the charged salt ions compete with the bound proteins from the charged region functional groups. Proteins with a few charge groups will elute at low salt concentration, means those proteins which have only few charge groups. Of course, they will elute out at low salt concentration. But those which have very many charge groups, they have greater retention time and will elute out later. Although less common, a pH gradient can also be used for the elution. What do we mean by this? We mean by this that we are changing the pH of the solution in a gradient form. Means with time we are changing the pH. Here a pH gradient is chosen that approaches the protein of interest pi. Means the pH will change as such that we reach the pi value of protein of interest. Means the protein that we want to finally purify from the sample. So as it will reach its pi, it will carry no charge, and when it will carry no charge, there will be no interaction with the column, and it will finally elute out from the column. In this process, we have two types of exchanger. First is cationic and second is anionic. In case of cationic exchanger, the matrix will be negatively charged and it will attract the positively charged cation. So the counter ion will be positively charged. My positively charged analyte will replace that counter ion and will bind to the cation exchanger. And then we will finally recover our target protein. Similarly, we have the anion exchangers which have positively charged groups to which negatively charged counter ions are binded, and my negatively charged analyte will replace these counter ions. This is how an anion exchanger works. You can see the matrix is positively charged. To this are binded the counter ions which are negatively charged. The sample comes and only the negatively charged binds and the positively charged are removed. When we change the pH conditions or the salt gradient, finally the less charge is removed first and more analyte with more charged groups will retain more, but then after finally it will also be removed from the column. Similarly, for the cation exchangers, the matrix is negatively charged and we have the positively charged functional groups added to it. This is like you can see here, the sodium is the counter ion and this is the charged molecule to be exchanged, so it binds and the counter ion is replaced. Now we have weak exchangers and strong exchangers. Strong exchangers, for example, means those remain constant over a great pH range. Those exchangers which remain constant, which remains their integrity over a good pH range are known as strong exchangers. For example, quaternary ammonium, sulfonate, sulfopropyl resins. Weak exchangers, they deliver their optimal performance only with a very small range. Means the pH of the buffer no longer matches the acid dissociation constant of the resin functional group. These resins suffer significant capacity loss. So we have weak exchangers like diethyl aminoethyl DEAE or carboxymethyl. These are important weak exchangers. Strong exchangers, as we already discussed, their performance remain unaffected over a considerable good pH range. Coming to the applications of ion exchange chromatography, this technique is used for deionization and softening of water, for the purification of solution to keep them ion free, in biochemistry for separation of drugs and metabolites from blood or urine, and this is used for separation of organic compounds, mixture of proteins, carbohydrates and nucleotides, for purification of enzymes after extracting from the tissues. So this was all about ion exchange chromatography.